Hey everyone, great to chat to you today about something that I've been working on the last couple of years. So a bit of background, my name is Josh, I work at Xanadu, which is a photonic quantum computing hardware company up north in Toronto in Canada. So we've been working really hard up in Canada to build a nanophotonic chip to do a lot of the quantum computation stuff that you've been hearing about in the previous sessions here at the Quantum Village. So maybe this talk's a bit of a different one. I want to tell a bit of a story about what we're building, what we're building when it comes to the software stack or the infrastructure that surrounds quantum computers. We tend to think about quantum computers being the hardware, the physical hardware that's doing the subatomic computation using a completely different type of physics compared to the normal computing devices we have. But the hardware is only part of the story. It's a very big, very difficult part of the story, but the software stack and the infrastructure and how we actually get the algorithms from a researcher or from someone doing the quantum programming down to the hardware is super, super important. So I'm going to tell a bit about the story of how we used to do this, how we still do this, and how we're thinking about doing this in the future. So how do we make LLVM quantum, or why you don't have to be a quantum physicist to build the programming stack of the future. So maybe taking a step back, I want to talk a bit about quantum software itself. So why do we need quantum software, or even what is quantum software? So quantum software is something that started to spring up like in the 90s, early 90s, 2000s. The main focus being we have a lot of researchers in this really, really difficult field. We need to make it possible for them to explore the algorithms that we can take advantage of with quantum computing. We need to make it possible for them to actually take these algorithms they're exploring and send them to these near-term, very noisy, very small quantum devices that were being prototyped. And I think this is a really interesting thing because we tend to focus on these big revolutions and these big conceptual changes in science. So general relativity and quantum physics is big conceptual changes in how we approach science as a whole. But a lot of what we've been doing over the past 100 years, there's been a lot of these tool-based revolutions. And these are revolutions where it's not so much the concept that's driving massive change in society and technology, but it's the tool that's resulting in massive change. So you can think of things like telescopes and astronomy. The invention of the telescope led to a revolution in what we were able to see in the night sky and the science and physics behind that. X-ray crystallography and molecular chemistry and biology. So in the 1950s, the ability to have a look at these structures inside the human body led to another revolution in what we're able to do in terms of molecular science. Another one, a more recent one, PCR, for the study and sequencing of DNA. These are all cases where tools that we had available to us led to a revolution in technology around us. And machine learning, I think, as well, is another really, really big one. So machine learning has been around since the 1980s, but it really took a combination of 3 different tools to come together before we were able to take advantage of this sort of machine learning revolution we've seen in the last 10 years or so. So we needed the algorithms. I think in the 1980s, lots of researchers were exploring algorithms like backpropagation from a theoretical point of view. The second tool we need is we need the accessible hardware. We need GPUs, we need TPUs, we need ways to efficiently implement these algorithms so that we can take advantage of this for building things like neural networks and for deep learning. And then that final tool we needed was the specialized user-friendly software. We needed tools like TensorFlow, like PyTorch, like JAX, to allow us to actually take these ideas that we're building, take these new concepts that researchers are coming up with every day, and see if they work in practice and have them run and scale up. So this is a perspective that I like to think about when we're talking about quantum computing, because quantum computing really is a tool like these examples I've shown here. The hardware is a tool. Once we have the hardware, we'll be able to experiment and do things that we were only thinking about theoretically beforehand. And then the software that builds the stack around quantum computers, that's a tool as well. A super, super important tool that a lot of people are working on right now alongside the hardware. So I want to talk a bit about what quantum software is. We know that it's a really important tool. Researchers are using it daily to sort of like explore the algorithms they want to run when the next generation fault-tolerant quantum computers are here. But what exactly is quantum software? So there's a large variety of quantum software in the ecosystem, and you just had a talk on Q# from Microsoft in the previous session. So that's another really good example of quantum software. We have Qiskit from IBM, Cirq from Google. NVIDIA has CUDA Quantum. Xanadu, where I work, we're developing Penny Lane, another quantum software package. So there's actually a very, very rich ecosystem of quantum software around at the moment. The open source quantum software ecosystem is massive, and if you go on GitHub and search quantum or quantum software and explore, you'll see a bunch of really active projects with researchers, with engineers, with computer scientists, all sort of exploring and trying to work out these problems we can solve in quantum computing. So I wanted to share a couple here, but then also talk about what quantum software is today. So there's a couple of things. Not all quantum software is like this, but there are a couple of things that is common to a lot of quantum software packages out there today. So the vast majority of them tend to be Python-based. So you're working in Python, whether you're in the terminal writing Python scripts or in a Jupyter notebook, and you're building Python-based scripts that have a representation of the instructions we want to send to a quantum computer. So on the right here, you can see I've got a code block. This is using Penny Lane, the quantum software library that I'm helping to build, the open source one that I'm hoping to build at Xanadu. And what this is basically showing is showing that we have a bunch of quantum gates, which you saw in the previous session. We have Rx gates, RY gates, C0 gates. These are the basic primitives that end up executing on a fault-tolerant quantum computer. This is kind of the assembly language of quantum computers. So what we're typically doing is we're working in Python. We have a domain-specific language in Python that allows us to represent these primitives, and we can submit them for execution. So we're programming at the level of quantum circuits. We need to know the gates that we want to implement on the hardware. We need to know how we want to pre-process them, and we need to know how we want to post-process them. We're also doing a lot of execution on simulators and hardware with today's quantum software. So I would say almost every quantum software out there is backed by a simulator. We need a way to very efficiently check what we're doing on small scales is working. If you're an algorithm researcher, you need to be able to verify, is this assembly code that I'm essentially writing, is it doing what I want my algorithm to do? It's a very tricky process, quantum algorithm development. So simulators are today still a very, very important aspect of quantum computing. At the same time, though, we do have hardware available. So a lot of these Pythonic quantum computing devices, quantum computing software packages, are also coming with the ability to execute on hardware as well. And I'll talk a bit about how they're actually doing that. So what happens when you execute this example that I have on the right-hand side here on hardware? So a couple of things happen. The first thing is that we have to optimize the circuit with runtime parameters. So we need to know all the information about the system. In this case here, I have Rx and RY gates that take in the parameter. So they take in the parameter D and X. We need to know what that value is so that we can begin the optimization. And this optimization is two things. We want to reduce the size of this quantum circuit as much as possible. We want to cut out as many gates as we can, because the more gates we have on noisy hardware, the output of the algorithm will be more noisy. There's another thing we have to do as well, though, which is we have to make sure that the gates that we're executing and on the qubits we're executing them on, we need to make sure they actually exist on the hardware device. And this is not often the case. Hardware devices don't always have all qubits connected to each other. At this stage, they don't always have support for all the quantum gates an algorithm developer might be doing. So we need to be able to convert what you see here to something that the hardware device will know to understand. And then the next step is we take the quantum part of just this program. So you can see that the program on the right is actually quite complicated. We have classical processing. We have a cost function that's doing things like taking the sign and the absolute value. We're taking expectation values of a measurement of this quantum hardware. This is all classical stuff, but what we actually need to do today is we need to extract just the quantum instructions. So we need to get just a list of the gates they're going to execute on that quantum hardware. and give that to the device. So we kind of need to separate the classical processing from the quantum processing. And then finally, once we've done that separation, we've got just a list of the quantum part that we need to execute. We typically submit this to a cloud-based REST API. So we're submitting this to a HTTP endpoint. So we're really, while you're working in Python and you're working with classical and quantum very much intertwined, when it comes to execution, we really are separating it out. And we're taking just the quantum and it's being executed very far away from the classical part of our program. So I can walk through this very quickly. So here's the example I had just previously. So I have a quantum circuit here. I got a for loop and an if statement. So depending on the data that I want to embed in my quantum hardware device, I might want to apply different gates on different wires. So that's the for loops and the if statement. So I have some classical control that determines what my quantum circuit looks like. I'm then taking an expectation value at the end of this, and then I might have a cost function. So I might want to do something like quantum machine learning, where I have a neural network, and part of that neural network just happens to be quantum in nature. So here I have my cost function that's executing the quantum hardware and then returning a value to myself. So on the right, you can see I'm creating some data and some weights. I'm executing this, and behind the scenes, a lot of classical and quantum processing is happening. And I get my results, or in this case, I get the gradient of the quantum circuit execution. So behind the scenes, what's happening? So the first step is we need to extract out the quantum information of the system. So behind the scenes, what will be happening is the program will be analyzed at runtime, and we'll be able to extract all the gates that are being applied as just a long linear list. So you can see here on the right, we have some Rx, Ry, and C0 gates. These are being extracted into a list of the Rx, Ry, C0 gates that need to be executed based on unrolling these loops and if statements at runtime. But that's not the full story. There's an additional part that needs to be done as well. I mentioned before that quantum hardware devices might have restrictions in terms of what qubits are connected to what qubits and what gates they support. So we need to now optimize this long list of gates with respect to what the hardware actually supports. So here's an example I've done on the right where I've chosen an IBM quantum device available through IBM Quantum Cloud. And this device supports gates, it supports a very small set of gates. The good thing is we know how to decompose the gates I have in my program here to the gates we need on the hardware device on the right. So we're able to do that computation. It can be quite computationally intensive, so the longer your program is, the harder the more work it might require to do this. And remember again, this is happening on runtime, so every time I execute this Python program, this process is going to repeat, even if it's the same circuit that it saw the last time. So this is currently the state we see quantum software in today, Pythonic-based, things happening at runtime, separating out the quantum and classical and having a very long list of quantum gates. But we can do a lot better than that, and we know from the research that we can do a lot better than that. So I've got a very quick example here. There's a Shor's algorithm. It's one of the most important algorithms in quantum computing. It allows us to do factorization of very large numbers using quantum hardware in cases we can't do in classical hardware approaches. So what I've done here, or the results I'm showing here, is we're taking Shor's algorithm and we're going through that same process. We're coding it up in Python, we're targeting a hardware device, and we're compiling it or decomposing the gates to match that hardware device so it can be executed on hardware. And what we actually find is that if we have a very flat representation of the program, so we actually just have a long list of gates and then we need to convert that into a long list of gates that works on the hardware, this can scale really badly. We can have almost n to the power 4 scaling just to convert this very long program into another, even longer program to execute on the hardware. But there's something we can do to fix this. So you might remember that in my initial Python version of the program, I had for loops and I had if statements, so the program was actually quite compressed. The really nice thing about that is we can preserve that. We don't have to remove those for loops and those if statements. If we keep that really compressed version, that dynamic compressed version of the program representation, we can still compile it. We can still make sure that that will run on hardware. And it turns out that this is just constant overhead. We suddenly lose this massive scaling that required compilation of that program before. And we now just have constant overhead to convert that program to one that we can then execute on hardware. So what this is telling us is that we can do better. It's not the way that quantum software currently works, where we're splitting up quantum and classical, doing everything at runtime and just having a long list of quantum gates. That's not the way we should continue for the future. We can do better in how we think about the quantum execution pipeline. So, can we do better than this? Something that is worth thinking about is that there isn't really such a thing as a purely quantum workflow. Almost any workflow we do, any algorithm we're thinking of, even if it's a textbook fault-tolerant algorithm, for example, there will always be an element of classical processing, whether that's setting up the circuit, whether that's preparing the data that you want to embed on the hardware device. So we can view it from the point of view that quantum workflows are inherently hybrid, mixing quantum and classical, and we should try and preserve that. We shouldn't try and separate that, but actually treat everything as a hybrid program and try and work out what infrastructure allows us to do that. So taking into account control flow, data loading, post-processing, even optimization loops. In quantum hardware, you can do mid-circuit measurements, measure the value classically, process that, and then feed that back into the quantum hardware while the hardware is still executing. So this is very much intertwined quantum classical that we want to be able to support. At the same time, another thing we can improve is that everything is happening at runtime in Python if you're using these Python-based quantum software libraries. So this is terrifying. We know that this is not the way that it needs to go, especially if we have programs where you want very rapid feedback between the quantum and the classical parts. We need to be doing this in a better approach. I spoke a bit about compiling quantum circuits, so optimizing the quantum circuit to run on the hardware. This is required, but it's hard, and it's currently happening every time we run the circuit with runtime values. So can we do any of this ahead of time? And then I think the biggest one as well is the way that we currently interface with quantum hardware. We've got a local Python instance on our laptop, perhaps. There's a remote HTTP REST API for a hardware vendor, and a server-side queuing system. So you submit just your quantum gates you want to execute, you wait in the queue. When your results are ready to be executed and you get your results back, then the Python side locally will take over and continue doing the classical processing. So we actually have very, very separated quantum and classical processing, which is not ideal for some of the things we want to be able to do with quantum computing. Yeah, and then I think finally, something which I mentioned is that very flat, unrolled list of quantum gates. If we have structure, we should preserve that structure, and we should keep that structure all the way to the end. So can we keep that structure as close as we can all the way down to the hardware control? That's one of the big questions for the infrastructure side. And this, I alluded to this slightly just now, but this is only going to get worse. So this is an example program, again, written in Python, where we have a mid-circuit measurement happening here. So we're applying a gate to the hardware device. We're then measuring that qubit. So at this point, this measurement M is actually a classical value. We can then do classical processing of this mid-circuit measurement value, and we actually feed that back into the same quantum execution happening at the same time. So this is terrifying if you think about that previous infrastructure, because you've got a queuing system where you're doing half the circuit, returning it to Python, post-processing it, and sending it back to the hardware device. And there's no way we can do this fast enough to be within the quantum decoherence time. So that's maybe another reason why we are focusing on quantum software right now. It's not just for researchers to explore and build algorithms, but we also need to work out how we support those meaningful algorithms that researchers want to run on fault-tolerant quantum computers. How can we connect what a researcher might want to run in 5 years with the infrastructure that will let them do that and run that on hardware in 5 years? So there's a couple of things we want to do now. We want to keep the quantum and classical together. We want to allow researchers to keep working in Python, at least for now. This is the language they're comfortable in, this is the environment they're comfortable in. So let's allow them to keep working in Python, but figure out how can we take that entire workflow, the quantum and classical bits, extract it from Python, and compile it down to something that's a lot more efficient. At the same time, we can work out, can we optimize the program ahead of time, at compile time? So we might not have all the information at compile time, but can we do something better than now, which is just waiting until runtime to do everything? So the question we then had, I think, as a quantum computing community is there existing classical compilation infrastructure with decades of development that we could utilize here? And when we looked around, the answer was, in fact, yes. It was the LLVM compilation stack. So this is a very big project. It's very heavily used, very important in a lot of other open source ecosystem projects. So it provides a common intermediate representation to allow us to target and compile lots of languages like C, C++, Fortran, for example. So there's another tool that allows us to pull in quantum and LLVM, and this is QIR, Quantum Intermediate Representation. So LLVM is very, very strong when it comes to compiling across the classical software ecosystem. The only thing it's missing is knowing these quantum primitives. So LLVM has no concept of a quantum gate or a quantum measurement, for example. And this is what QIR brings to LLVM. It's an extension that provides LLVM primitives so that you can define quantum instruction sets such as gates, qubits, measurements directly inside LLVM. So the ingredients are kind of coming together to utilize this very strong open source ecosystem, LLVM, for quantum compilation and hybrid classical quantum compilation. The final thing I think that was launched about 2017 is MLIR. So MLIR, multi-level or multi-layer, I always forget, intermediate representation, is a project I think founded by TensorFlow, PyTorch, to have a higher abstraction intermediate representation that they could use with LLVM. So have something a bit more high level where they could keep some of the abstractions that they need for linear algebra and for tensors so that they could integrate better with the ecosystem without having to drop very low level into LLVM and do very low level computations. So these three pieces, LLVM, QIR, and MLIR, they're the tools I think that is starting to allow us to make LLVM quantum. And now I'll chat a bit about how we're actually doing that. So QIR launched around, I'm trying to cast my mind back, I think around 2017, 2018, spearheaded by Microsoft, and this was the first quantum instruction set for LLVM. So the next stage, early MLIR dialects, this MLIR was introduced 2017, and I think 2021, 2022, this is when the quantum community got very excited because they realized that this is actually a really great place where we can play around with quantum dialects of LLVM, but have it be fully compatible with the existing classical dialects and classical infrastructure. The really nice thing about MLIR is not only that it's higher level abstraction of LLVM, but it has multiple dialects that you can define that can interact. So you can define a quantum dialect, you can define a linear algebra dialect, you can define an auto-differentiation gradient dialect if you want to do machine learning. And there's very little work, or almost no work, to allow these to interact together in one person's program or workflow. So, and we're starting to see industry adoption of this now. So some examples, NVIDIA's CUDA quantum toolkit is using MLIR, LLVM, QIR under the hood. This is sort of next generation quantum software beyond that sort of Python separated quantum classical I was talking about before. QCore is another example of this coming out of Oak Ridge National Labs from the United States. And Catalyst is an extension that we've been working on at Xanadu using the same sort of technology. So LLVM, MLIR, and QIR. So it's very much early days, lots of exploration, lots of R&D to do. The sense so far is that this makes sense for the future. This is the stack that will carry us towards those fault-tolerant quantum computers over the next 5 years. but still a lot of work to do, still a lot of questions that we need to answer here. For those of you who might be familiar already with quantum software, I want to briefly talk about that quantum assembly I mentioned again. So earlier on in the talk, I showed that list of unrolled gates that would occur if we sent the program to IBM Quantum. So that was using a human-readable intermediate representation called Open Chasm. And you can see that Open Chasm here again on the left. And this is what a majority of the quantum software ecosystem is using today. So it's a textual description of the circuit. It's got very limited classical instructions and dynamicism, and no in-memory representation or transformation infrastructure. So on the right, we have sort of a diagram of MLIR and LLVM, and kind of representing that you can have these existing classical intermediate representations that are used in a lot of programs already today. And you can accommodate multiple domain-specific abstractions side by side. So the question that we always encounter is, why use LLVM? Why not just take something that already exists in quantum, like Open Chasm, and add classical program support to that? It's a good question, and we could definitely do that. I think it comes down to, do we want to add classical compilation to an existing quantum stack, or do we want to add quantum support to an existing well-developed classical stack? And the sense at the moment is it probably makes more sense to take something like LLVM that's very well developed and try and add quantum to that. And this is also another example just showing LLVM on the left. So this is the intermediate representation of a very simple function that I think is just taking two integers that has a for loop and it's adding them together. So here we have standard LLVM on the left. And on the right, we have the MLIR representation of this. I'm not a LLVM programmer, so I can't walk through the technical details of either of these, but I really like this example because it just illustrates that when you have something very simple, while the underlying LLVM intermediate representation might be complex, MLIR provides a very nice sort of higher abstraction place where we can think about these and reason about them without getting lost in the low-level specifics. So I can talk a bit about how we're actually using these technologies at Xanadu. So we've created a tool called Catalyst. It's open source, Apache 2.0, very experimental, a bit R&D. And the goal is essentially to cover the things I mentioned before in terms of how we can make quantum software better. So what we're doing here is we're taking an approach of quantum just-in-time compilation, where you take a program that's written in Python, all of it, the quantum parts, the classical parts, we capture that and we lower this down into LLVM and compile this to a binary that can actually be executed very close to the quantum hardware itself. So it allows you to write these hybrid quantum classical programs that we know all quantum algorithms are essentially going to be inside Python using Penny Lane, our quantum software programming toolkit, and compile this down to a binary that can be executed close to CPUs, GPUs, and QPUs. So you can get this very fast feedback between the classical and the quantum parts. So a very brief example here, but what essentially is happening is that if you so we have this QJIT decorator. This is essentially quantum just-in-time compilation. If you remove this QJIT decorator, the same thing happens as I mentioned before. All these for loops and if statements are unrolled at runtime. We end up with a very long list of quantum gates, and this is executed through serialization on the cloud API. With this QJIT decorator, we actually preserve this. So we capture the for loops and the if statements at compile time. We then optimize the program for the hardware at compile time, leaving these for loops and if statements intact. And then we have a binary that we can execute close to the hardware. And these for loops and if statements will be interpreted at runtime. So you can get, even just with small programs, you can see a significant speed up almost purely from just, this is no longer actually executing in Python anymore. But it goes a bit bigger than that. So you can actually, that was a very simple example of just a quantum circuit with some classical pre and post processing. But you can actually build very, very large workflows. You can build workflows where you have multiple quantum circuits that have a for loop around them or optimization loop around them. You can have a workflow where you have a quantum circuit that has an output that then goes into the input of another quantum circuit. you can quantum just in time compile all of those, the entire workflow. And that's essentially what we want. We don't want to think about the quantum and classical being separate anymore, but we want to consider the whole thing and see how we can get that running as fast as possible on the hardware. So a bit of technical details about what's happening under the hood. Something I didn't mention before, but the quantum software tool that we build at Xanadu, we have a very strong quantum machine learning component. We have a very strong quantum machine learning research group, and I think I'll talk a bit more about this tomorrow. But one of the side effects of this is we try and make sure that our software is always fully differentiable. So anything you write in it can be differentiated end to end in case you want to optimize or train any part of it for machine learning purposes. So what we actually have here in this example, and then under the hood on the right, we're first using Python and JAX, which is a machine learning library from Google, to capture all the classical and quantum processing that's happening in Python. We're then lowering this down into a mixture of different MLIR dialects. So we have a dialect for the quantum instructions, a dialect for representing gradients, a dialect for representing control flow around quantum operations. This then gets optimized and compiled down to a binary using LLVM and QIR. And then we have various runtimes that we're exploring that can execute these binaries, and it knows what the quantum instructions, or where the quantum instructions should be executed. So this is a bit just showing sort of what this stack looks like behind the scenes and what all these where all these different pieces of technology are being used, the Python, LLVM, MLIR, and QIR. And it's super interesting as well to see the different intermediate representations as you go through this sort of like next generation quantum software stack. So we're initially capturing it in Python, so you have this JAXPA representation. This is just a representation that's used by this JAX machine learning library. And you can already see there's a combination of classical processing and quantum processing happening in here. It then gets lowered down to MLIR, where we're still able to preserve this mix of quantum and classical. So at this point, we've now entered the LLVM compilation stack. So we're out of Python. We have a compile time representation of this hybrid quantum classical program. So not everything about the program is known yet. We know the structure, we know the gates. We don't necessarily know the runtime parameters. So we're trying to compile at this point as much as we can without knowing what the runtime parameters of the program are. And then finally, LLVM and QIR. So this is the lowest level intermediate representation we get to. This goes on, so I think the previous two slides, it stayed on the slide. This slide, it's so long, it goes for slides and slides and slides. So this is maybe 10 or 20% of it. And I just want to finish here showing another example of a hybrid quantum classical program. And this is an example I really like, because this is one that we can't actually run in our previous quantum software stacks that separated the quantum and classical. The reason I really like this, and the reason we can't currently execute this, is because it's doing something called, it's got a while loop, and a while loop around quantum measurements. So what's happening in the circuit is we're applying some gates to entangle all the qubits, and then we're measuring the first two qubits. And so what we do is we prepare all three qubits in an entangled state, we measured the first two, and then based on some condition of these first two measurements, we continue. So you continue doing this prepare and measure subroutine until those two measurements you get satisfy some condition. This is something that we can't run in the old style approach, right? Because if you separate the quantum and classical, you just can't reason with such a program. We have a while loop here that's unbounded, and it depends on information that happens midway through the quantum circuit. So this is a program that kind of emphasizes why we need to think about this new approach to quantum software. And with the LLVM style approach here, we actually can execute this. So we can capture this, compile this down to a binary, and execute this on the hardware, with hardware that supports mid-circuit measurements. Something else I want to mention as well is that it's not just quantum software people thinking about the high-level infrastructure here, but quantum hardware developers are increasingly exploring the LLVM stack as well. So the LLVM and MLIR stack. So I've got a couple of examples here I could pull from the internet. But Oxford Quantum Circuits, they have a package called Rascal, and this is a LLVM-based runtime, so very similar to the approach I was showing before, where it can take LLVM QIR intermediate representation input and execute this, and compile this and execute this on their hardware. Rigetti has been exploring a QIR-based compilation stack as well for their hardware devices. And IBM actually has a video online at the LLVM conference where they're talking about what their infrastructure looks like, and it is also using this MLIR approach for capturing the user's program and then compiling it down to a binary to run on their control systems. So that's a brief introduction to how we're actually making LLVM quantum. There's still a lot of work to be done. So we still need to work out how best to integrate this with circuit compilation. As I mentioned before, we sometimes don't know all the details of the circuit at compile time. So how can we reason with this? How much circuit optimization can we do at compile time when we just don't have all this information yet? There are lots of other questions here when it comes to compilation, which is how do we best optimize the circuit without unrolling the for loops? We could unroll the for loops, but then we know that won't scale. So we want to do as much as we can while keeping that classical control flow in place. There are big questions on the horizon when it comes to things like error correction. So error correction is sort of encoding in a level of redundancy into the initial program and then having a decoder that acts in real time to measure the hardware and correct these errors as it sees them. The LLVM stack, as I present it today, seems like the infrastructure that makes sense for this, but we're not really sure how or where. Where does the error encoding happen? Where does the error decoding happen in comparison to the stack here? And then the big question, what does the infrastructure look like in the future when we're integrating with fault-tolerant hardware? That's also a really big question on the horizon. So just to summarize, there's been a big shift in quantum software over the last 2-3 years or so, where we're seeing the community moving away from sort of static, separate quantum classical execution towards more dynamic hybrid quantum software stacks that use LLVM by adding quantum instruction support into LLVM itself. The paths we take now are going to define the software paradigm of the future. We don't know all the answers now, but we're figuring them out as we go along, and you don't need to be a quantum physicist to help us figure these out. Where we're going, we don't know the answers, and this is a field that's been dominated by quantum physicists for a long time, but it's increasingly looking like we'll need experts in compilation, we'll need experts in LLVM, we'll need experts in big parts of these compilation stacks that we're beginning to use as a quantum ecosystem. So just a quick call to action to help us get involved, contribute, and build this next generation of quantum software. The stack that I mentioned before, Catalyst, it's all open source, it's work in progress on GitHub. Feel free to jump in, play around with it if you'd like, to hack it a bit, make pull requests, and then our documentation has a lot more technical details as well behind the topics that I was discussing here. So the documentation goes into a lot of depth about MLIR quantum dialects, about how we do transformations on them in different situations and things like that. So thank you, everyone. I hope you enjoyed the talk. Yeah.
So I'm actually an LLVM compiler engineer, so this is really interesting. My question is that do you think in the future you would create a quantum backend rather than just MLIR? MLIR is pretty high level, but at the end of the day you need like 0, 1, and qubits, I guess.
Yeah.
What are your thoughts on that?
Okay, so the question is, would we consider building an LLVM backend in the future for quantum?
You know how there's like x86, ARM,
Yes.
LLVM backend, so
Yeah, it's definitely something that has been on our minds. I don't think anyone has explicitly done this yet, except potentially Intel. I know Intel released a paper a couple of years ago where they have this ELF-Q format. It's something that has been on people's minds. We've definitely talked about it internally. Does it make sense to have a quantum instruction set backend for LLVM? At the moment, we're not exploring it just because we think it's too early. We might need more standardization in the system yet. We might need to explore some of these infrastructures a bit more. At the moment, when we talk about interfacing with quantum hardware, we really mean interfacing with the classical hardware around the quantum hardware. So like the systems that are controlling the lasers and things like that. And these are very different for different quantum hardware devices. Yeah. Yeah. So the question was, are we considering exploring early fault tolerance in this infrastructure, in the early fault tolerant regime? And the answer is yes, but in a very sort of exploratory and R&D approach. I think there are still a lot of questions. We don't know where it makes sense for error encoding to live in the stack. We don't know where it makes sense for error decoding to live in the stack. It's something that we've been thinking about internally, and you can place these components in a lot of different places and see a lot of different pros and cons. So I think the way we are going to approach it is by exploring simple proof of concept, error correction codes, things like surface codes, things like that. MBQC as well, which is quite relevant as well to the hardware that we have at Xanadu. So start off with exploration prototypes and see from there. But unfortunately, we don't really have a clear answer to where we would build this into the stack yet.
All right, this is a quick question. Really quick. Okay. Do you have a placeholder for more exotic hardware, like quantum annealer or adiabatic?
So the question is, do we have a placeholder for more exotic hardware, like adiabatic hardware or annealers? At the moment, no. At the moment, I think the stack assumes that it will be a qubit-based device as an output. But things will change over time.